Okay, in an earlier video, well, the one that immediately preceded this one, we had the 2x plus 5 quantity squared, and I did this. Now, there's a strong temptation to do 2x plus 5 squared equals 4x squared, which would be the square of 2x, plus 5 squared, which is 25. And that's clearly wrong. Okay, so the problem is that people see something of the form a plus b squared and think it's a squared plus b squared. Now, there are ways to prove or disprove this. The easiest way to prove it is just write out a plus b times a plus b and use the distributive law, and you're going to get a squared plus 2ab plus b squared, which is kind of a familiar formula anyway. Okay? But it's not a squared plus b squared. You got that 2ab in there. And everybody should understand that, but let's test. The common illusion or superstition that a plus b squared equals a squared plus b squared. Okay? Using simple numbers. And this is like, I think it's objective 5, if I'm not mistaken. Yeah, verify the plausibility or disprove statements. Okay? So this is like objective 5. Okay, so if you're tempted to do this, you can say, well, okay, let's see, 2 plus 3 squared then should equal 2 squared plus 3 squared. Now, 2 plus 3 squared is 5, 2 squared is 4, 3 squared is 9. So you get 25 here and obviously get, no, you don't get 25 over here, do you? You get 13. Okay? This disproves a plus b squared equals a squared plus b squared. Now, just comment, not part of objective 5, but a plus b quantity squared is a plus b times a plus b. It's not a squared plus b squared unless this multiplies out to give you a squared plus b squared. And that equals a times a plus b times a plus b using the distributive law, which is a squared plus ab here, and b times a being b times a and b squared. That b times a is the same as a times b, so that's a squared plus 2ab plus b squared, not a squared plus b squared. Now, you don't want to make your numbers too simple. If I'd have chosen 2 and 0 here, it would have worked out. Because, of course, b squared would have been, well, you can work it out. That's with 2 and 0. So we don't like to use numbers like 0 and 1 in doing these things because you can get misleading results. So if we'd have used 2 and 0, it would have come out the same, but that would not have proven whether this is in general true. It only proves that it's true for 2 and 0. And of course, it's true for any number in 0, but not for any other pair. Okay? So you got to be careful. So that's just an example, and you've seen other examples. Like you can prove that x to the 2 plus 3 equals x to the 5th. Well, that'd be an example of x to the a plus b. And that's not even what I wanted to write down. Of course, it equals x to the 5th. Now this is something you should know, but in case you don't, this is an example of the rule x to the a plus b equals x to the a times x to the b. Okay, so we've got x to the 2 plus 3 equals x squared times x cubed. This is an example. This means that x to the 5th would equal x squared times x cubed. I'm going about this in a little bit of a clumsy manner, but we need a number for x. Well, let's choose an easy number for x. Let's let x equal 2. That would be 2 to the 5th equals 2 squared times 2 cubed. And 2 to the 5th is 2 times 2 times 2 times 2 times 2, that's 32. 2 squared is 4, 2 cubed is 8, 32 equals 32. Okay? At this point, we would say it's plausible that x to the a plus b equals x to the a times x to the b. We haven't proven it. And to prove it, you really got to say that, okay, x to the a plus b means you write x times x times x times x. And you write out a plus, this string would be a plus b x's long. And then this would equal x times x times x, x multiplied by itself a times. And this would be b times. Well, if you got a of them here and b of them here, how many of them do you have? You have a plus bx's there, which is what you have on this side. So it must be the same. And that would prove it. Now that's not really part of the objective, but I thought I'd toss that in. Okay, so people do quite well with this sort of thing, just plugging in numbers and testing whether something is true or not. Of course, want to kind of extend that and actually use it in practice if you need to test something. Because you can usually pretty easily disprove a wrong piece of algebra using simple numbers. Not always, but usually. So it's a handy thing. It also gives you an idea of why things are so.